Alright, so in this video what we want to examine is rotational motion. So what we want to do now is we want to build a set of kinematic equations that help us describe the rotation of an object about its central axis. So the idea is whenever we want to talk about rotation, we need to talk about how the object is changing its position. And so whenever we have rotation and we're talking about changing positions, instead of using like a position as in an X and a Y, what we'll do is we'll describe our location based on an angle. But in order to do that, what we need to do is we need to mark a place that we're going to measure our angle from. And normally whenever we want to talk about measuring an angle, what we want to do is, if this central dot here is our rotation point that we're rotating about, so our ball is rotating about that central point, you can think of drawing an XY axis through the center of the object around which everything is rotating. Then if you're thinking in terms of like X and Y, then we always measure the angle, let's say we'll call our angle theta. We measure theta up from the x-axis counterclockwise. And so the idea is that we always pick this x-axis as the relative origin, and we measure our angles counterclockwise from that axis. So the next part we need in order to understand our motion of our object is we've said that we mark our location by some angle, and we said we measured that angle from the x-axis counterclockwise. Now the other thing we need is we need to mark the location from the center, and we do that by marking this what we have is this gray line in the slide, and I'm going to color it red. I'll color it green. This green distance here that connects the origin to the object or the point of interest of rotation, we're going to call that R. So the two things that we use to describe our rotation is we need R, which is the radial distance from the center of rotation, and you need that angle theta, which is your rotation position. Okay, so now we have R and theta. So this R theta system, just in case people haven't heard of it before, it also comes by the other name of polar coordinates, where R marks your radial distance and theta marks your angle. And then there's conversions you can do using trig to mark your X and Y. So if you're thinking about this in terms of trigonometry, what happens? You can think of this as some kind of XY, where your X position, converting over, your X position is R cosine theta 1, and your Y location is R sine theta 1. And so you can convert between X and Y and R and theta using this polar coordinate location system. But it's much simpler to describe everything in rotation. When you're rotating, it's much simpler to describe everything in terms of R and theta. So what we want to do now is we want to begin to rebuild our kinematics, but doing so using rotations and angles. So let's do this. Let's assume that our object is rotating at some rate, and initially our ball is located here. Initially our ball is here at some angle. This is theta 1. Right, so this is theta 1 initially. and then a little bit later the ball has rotated through to this new position, theta 2. So when you want to describe the ball's change in position, what we do is we say that the ball changed from theta 1 over to theta 2. And then the delta theta, or the change in theta, becomes theta 2 minus theta 1. So if you have a positive delta theta, you rotated counterclockwise. If you have a negative delta theta, you're rotating clockwise. And the positive and negative just tells us, so positive is counterclockwise and negative is clockwise. And so the idea is that when your ball is rotating, it starts at some theta 1 and moves over to theta 2. And that's our delta theta, or a change in position. Because your r is fixed, and we're always going to assume that our r is fixed when our things go around in our circles. We won't worry about changing r. So when we do this change, because we measure theta 1, as I said, from here, and now we have over here, you can see we have this new theta 2. Well then, as we said, this delta theta is the angle between this line and this line. That's delta theta, because it's the change in from theta 1 to theta 2. Now, what we want to do is we need to define what we're actually going to use our angles as. Most people are used to using degrees, but when we talk about angles in physics, what we need to do is we need to use radians. So our radians, when we're thinking about our axis, we measure angles this way. As you're going counterclockwise, the first thing you reach is you reach pi over 2 on the y-axis. You reach pi over here. This is 3/2 pi. And then you come back over to here, and this is 2 pi. Well, pi over 2 is the same as 90 degrees. Pi over here is the same as 180. 3/4 pi is your 270. And 2 pi is 360. So whenever you need, if you have to convert, you can just remember that you're running a full circle. A full circle is 360 degrees. So your full circle is 360, but 360 is the same as 2 pi radians. So whenever you need to convert from degrees to radians, you would take whatever degrees you have and you multiply by 2 pi, divide by 360, because there's 2 pi radians per degree. And that'll allow you to cancel your degrees, and your new unit will equal some number of radians. So if you have to, you can think in degrees and then convert to radians if it makes you, if it helps you out. But the conversion is you multiply by 2 pi and divide by 360 to convert from degrees into radians. Now, when we're thinking about our angle change, when we move our angle from theta 1 to theta 2, when we go from here over to here, our object does cover a linear distance. And that linear distance is called s, the arc length. And the arc length here is essentially that linear distance s is the arc length. It's related to r times the delta theta. So as r gets bigger, if r was out here, let's say your r was much larger and r was way out here, and you swept out this is the same delta theta, but this R2 then would have an S2 of R2 times delta theta, and this S is this S2 out here is much larger, even though it's the same angle, but because R2 is bigger, you had to cover a larger distance. And you can think about this because of people running on the track. These would, like in here, these are like the inside runners, the inside runner, it's supposed to be two N's, it looks like an M. Let's try to correct that. So this is the inside runner. I am struggling with my N. Okay. Runner. Okay. And out here is your outside runner, outside track runner, lane runner. Now, if these two people were going to cover that same arc length, let's say they were going to cover the 200 meters going around the curve, well, you know the guy on the outside lane, to keep up with the inside lane, has to run faster because he's covering S2 is larger than S because his radial distance is larger. But this is how we calculate. This is our first relation between this S is a linear distance. That's our linear distance, and delta theta is our angular distance. So this is a relation. This is how we relate linear to angular. They're related through R. All right. Now, when we want to talk about the rate at which we change our angular positions, this means we need to introduce something called angular velocity. Angular velocity gets this Greek symbol omega. So angular velocity is omega, and just like we said linear velocity was our delta x over delta t, omega is delta theta, right? Your change in angular position over delta t in some change in time. So you can think about initially being at some theta 1, you end up at some theta 2 later on in time. You have some delta theta from theta 1 to theta 2. So you have some delta theta. And your delta theta, the rate at which you do that, how much time it takes, you divide your angular position by delta t. That gives you your omega, your angular velocity. It's the rate at which you rotate or sweep out your angle. So what happens is we normally have theta 2 minus theta 1, and of course if we can go into the stricter definition using the calculus limit, the limit of delta t going to 0. So as your delta t becomes smaller and smaller and smaller, then you end up taking this d theta dt, and that becomes then the definition of your instantaneous omega as delta t becomes very small. Just like we saw with velocity, this was our average, and then as we shrunk delta t very small, we came up with our instantaneous. And just like we saw with theta, changing theta, if you have, we call counterclockwise positive and clockwise is negative, because it's the same idea. If the delta theta change is positive, you're going counterclockwise. If the delta theta change is negative, you're going clockwise. And so omega is related. Omega is just like we had linear velocity, omega is the angular velocity. Now, just like before, we have angular velocity. Well, there's a rate at which you can change your angular velocity, and that's called angular acceleration. And angular acceleration gets the label alpha. And alpha would be like if you were at this point and you had some omega 1. So at some point in time you have an omega 1, and then at some later point you have an omega 2. That means you changed from omega 1 to omega 2. And that means when you change that and you do that in some amount of time, you get an alpha, which is a change in angular velocity in time. So alpha is just like our acceleration, but it's for angular quantities. Now, just like when we had velocity had an average and then it had an instantaneous, alpha is the same way. If delta t, if the time interval between measuring your omegas gets very tiny, then you get down into your instantaneous alpha, and you then have this rate. The rate change is your derivative of that line at the point. And of course, if alpha is positive, that means your system is increasing speed counterclockwise. If alpha is negative, that means you're slowing down and your omega is getting smaller. So just remember that. We talk counterclockwise means that your omega is speeding up. Clockwise, if alpha is negative, that means you're trying to slow it down and bring the thing to a stop, or it's having an acceleration in the clockwise direction. So what we want to do now is we want to examine the linear relations between our omegas and our velocities and things like that. We already set up our first one by saying that S is related to R delta theta. And what happened when we did that, we said that this arc length was related to R times that theta, and we said that as R gets bigger for a fixed delta theta, S will get bigger. So that's the relation between angular displacement and linear. So remember, we said that this side is linear and this side is angular. And the relation between these, how you relate these two, is through this R. And so what you can think about is we can think about dividing through both sides by delta t. And when we do that, we're going to get delta S over delta t is equal to R delta theta over delta t. Because R is fixed, it doesn't change in time, so the only change that we have on this side is in our theta. So we can set up this relation by dividing we can set up this by dividing this thing by delta t on both sides. And we get this new relation. Well, what is actually delta S over delta t? This is our definition of velocity. And what's delta? This was our definition of omega. So really what we get is that V equals R delta theta over delta t, and that's really that V equals R omega. So this is how we can relate velocity to omega. We relate the linear again. The linear relates to the angular, and it does so through R. And this, going back to our runners on the track, we know that if someone's running further out here and they're matching, and we just like we said, if S2 out here is bigger because it's a bigger R2, delta theta is the same. These two delta thetas are the same, and R2 is bigger than R2 is larger than R. Then if they're going to cover these, if these things are rotating at the same rate, that means the V out here, V2, must be larger than V1 because this person has to cover a larger distance in the same amount of time. And that's related through the R. Okay, so now what we want to look at is we want to look at the acceleration. If we're changing omegas, we want to look at how these relate. Now remember, the tangent acceleration is this part here is tangent to the circle at that point. And the tangent one is responsible for the linear speed change. And the radial is the one that's holding us to the circle. And so what we want to think about first is that when we can start with our other line, remember before we said that V was equal to R omega, so we can take this line and then divide by our delta t on both sides, but remember R is fixed. And so what happens is we get our delta V over delta t, but this is just our tangent acceleration. And of course, omega divided by t we've said that alpha is delta omega over delta t. So essentially we get AT is R this, but this essentially becomes alpha. So we get a relationship between, again, this linear piece and the angular piece, and they're related through R yet again. And that's because as you're rotating this piece, the accelerations have to be larger. The tangent acceleration has to be larger the further out you go, because you're maintaining that rotation rate. Now the last one we have to think about is the radial piece, and or the centripetal piece. But the centripetal piece was related through v squared and r. But we know that v is equal to r omega. So we can substitute that into there, and we get r squared over omega squared. And so what we see is that the centripetal or radial acceleration is related to r squared over omega. It's still, the centripetal piece is still related to the v. It's not related to alpha, it's related to omega, but it's related through r still. There's still an r relation through r. But it's not related to alpha, it's related to omega squared. Now the last thing we can do is we can calculate this total acceleration vector A, because that acceleration vector, we would say that a squared is equal to at squared plus ar squared, because it's a triangle. These form a triangle, and we know that a squared equals b squared plus c squared, so we can take the square root of both sides, and then you get this. But we know what at and ar are. We said that at was r alpha, and we said that ar was equal to r omega squared. So we can substitute these in for here and here. Well, bad line. So what we can do is we can substitute AT into here and AR into there. When we do that, we then get this line here. But we can factor this out and this out, and we can get these two guys factor out to make the R, and we're left with that the total, the acceleration of this particle, if it's increasing speed around the circle, and as it's increasing speed, it's going to affect both the tangent and the radial piece. The total acceleration on the particle is r times the square root of alpha squared plus omega to the fourth. So this is the total acceleration on the particle as it's going around the system. Now the last slide that we have in here is essentially for looking at the linear. This side is all the linears, and then here is the rotational or angular equivalence. And for every equation you had in the linears, when we talked about kinematics and motion in 1 and 2D, you have the rotational equivalent. And so this is just a good summary slide for us to stop on when we were studying our rotation. So we have, just like before, we have our rotational, as we have, if you start at some initial velocity, you then, if you apply an acceleration, you change your velocity and you have some new rotational velocity. You have your equation that tells you that if you had some initial angle and you had some initial rotation speed, you apply an acceleration, 1/2 at squared, in this case it's alpha, you'll have some new location after some amount of time. This equation, the third one, this one gives us an angular position and it relates our angular position to our acceleration and our speeds. And then the last one is just the one with using the average omega. You're using the average omega of the system to look at your position and how it's changing. And so we have, for every linear equation that we looked at earlier on, we have a rotational equivalent.